Training your machine learning model is relatively straightforward in Edge Impulse. Once you've finished extracting features, head to the Neural Network Classifier page. Here, you can configure the model and training process. These are hyperparameters that we can tweak to hopefully make the model better. Each time the training algorithm makes one complete pass through all of the training data with backpropagation, updating the model's parameters as it goes, it is known as an epoch. Here, we can adjust the number of epochs for the training process. Let's leave it at the default for now. The learning rate controls how much the model's internal parameters are updated during each step of the training process. The minimum confidence rating is not used during training. Rather, when training is done and the model is tested with the validation set, any prediction with less than this amount is labeled as uncertain. We'll also leave this value at the default. Finally, let's look at the neural network architecture. This is a fairly simple three-layer neural network. Each layer consists of a set of fully connected nodes, or neurons. Another name for fully connected is dense. Let's take a closer look at this neural network. We start with all of the features that we talked about earlier. These should be the exact same 33 features that we extracted previously. The first layer of the neural network consists of 20 nodes. Remember that features are just numbers. In this case, our input features are stored as a 33-element array. Each element is copied to each of the nodes in the first layer. Each node then performs the necessary math on its inputs, which involves multiplying each input by a weight, adding in a constant known as a bias term, and summing them all together. The sum is then passed through a nonlinear function, the rectified linear unit in this case, to give each node its decision-making ability. This output is then copied to every node in the second layer. The process repeats again, but with a different set of nodes. The outputs of these nodes are copied to one last layer. There is one node for each possible class in the output layer. Since we have 4 classes, there will be 4 nodes. The same math is performed with the weights and bias terms, but instead of the rectified linear unit, the summation of the nodes is sent to the softmax function. The softmax function converts all of these outputs into what is essentially a set of probabilities. Each probability must be between 0 and 1, and all of the probabilities must add up to 1. From here, all we need to do is look for the output with the highest probability. For example, if P3 is the highest, then we can say that the model is predicting that the input features belong to class 3. You can click the Edit button if you would like to change the number of nodes in each layer. You can also add or remove layers to change the shape and size of the neural network. For now, let's leave the neural network at its default shape and size. After working through this demo, feel free to try a number of different layers and nodes to see if that changes your model's accuracy. All we need to do now is click the Start Training button. While the model trains, let's talk about that process. The exact techniques to train a neural network can vary, but here is a simple way to think about what's going on. We take our first set of features that we computed from the first training sample and feed that to the model. Remember that we have a label associated with each training sample and, as a result, with each set of computed features. Usually, the parameters in a model will begin in a randomized state, which means that random values were chosen for all of the weights and biases. The model will perform a forward pass, or forward propagation, which means it will perform all of the calculations we talked about a minute ago and give us a prediction. Because the parameters were completely random, the prediction will likely be way off. Another mathematical formula known as the loss function, or cost function, assigns some kind of penalty value for the model predicting the label incorrectly. This loss, or cost, is just a number and represents how off the model was from predicting the true label. The higher the loss value, the worse the model is at predicting the correct label. This loss value is then used to update all of the parameters in the model in a process known as backpropagation. This process continues over and over again for all samples in the training set. Recall that each time we go through all of the samples in the training set, it's called an epoch. Over time, the hope is that the model gets better and better at predicting the labels and the cost value goes down. If you were to plot the loss value over time, usually measured at the end of each epoch, you should see them drastically drop as the model becomes better at predicting labels. Normally, you will see the loss value converge to some number, as rarely the model will be perfect at predicting the right answer every time. If you were to plot the accuracy, meaning the percentage of time the model guessed correctly over time, you'll usually find that it's inversely proportional to the loss. That's because we expect the accuracy to get better over time as the loss drops. When the training process is complete, take a look at the output. The loss and accuracy should behave just as we discussed. Loss will drop considerably in the first few epochs and then level off. Same with the accuracy, but in reverse. The model starts out being quite bad at predicting, and it gets better very quickly. For our simple controlled example, I would expect the model to predict the classes nearly perfectly. You should also pay attention to these validation loss and accuracy readings. If you remember from a previous lecture, we talked about how you can set aside both a test set and a validation set. In Edge Impulse, we've already set aside the test set when we collected data. When you click the Start Training button, Edge Impulse randomly chooses 20% of your training data and puts that aside for validation during the training process. After each epoch, the program will perform a forward pass of each validation sample. Just like with the training samples, the model will take the features and attempt to predict the associated class. We use the same loss function as we did during training to calculate the validation loss. However, we do not use this information to update the model's parameters. Otherwise, this wouldn't be a validation set, it would be part of the training set. Like with the training set, we can plot the loss and accuracy. We expect to see the validation loss and accuracy follow a similar pattern to the training set's loss and accuracy. We can use the validation set to see how well the model can generalize to unseen data. If the model is better at predicting labels with the training data than it is at predicting with the validation data, that means the model has likely been overfit to the training data. We'll talk more about how to spot and fix overfitting in a later lecture, but know that the validation set is very useful in spotting this issue. You would normally expect the training set loss to be a little higher than the validation loss, but that's not always the case. Here, it looks like the model is a little better at predicting the validation set than the training set. However, that does not mean the model has perfectly generalized to our data. It could have gotten lucky with such a small sample set, which is why it's always helpful to use as much good data as possible. The real test will come when we use the test set. If you scroll down, you can find a confusion matrix, which shows the predicted versus actual classes from the validation set. We'll talk more about how to read and analyze a confusion matrix in another lecture, but it looks like our model did very well at predicting the motions.